all. Today we're going to be looking at improper integrals. Before we get started, I wanted to talk about a particular improper integral that's very fascinating right here. This is called Gabriel's horn, and it is the surface of revolution when you do the 1 over x function across your x-axis, and so it's forever going to the right. And the crazy thing about this is that it has finite volume. So the volume, when you figure it out, is actually pi. But when you try to figure out the infinite surface area, or the surface area, it's actually infinite. So think about this object who has finite volume. It goes on forever this way, but it has an infinite surface area. It's kind of mind-blowing. So that is called Gabriel's horn, and that is an example of an indefinite integral that we're actually going to deal with today. So for the definition of an improper integral is it has a pi where we're used to having our bounds. So we call that an improper integral, and we can actually break double in improper integrals like this up from negative infinity to 0 and then plus from 0 to infinity. And again, we're thinking about this as area underneath this curve. So a lot of times we're adding up an infinite area, but it actually approaches a value. So this is our example that we have here where we're going from 1 to infinity. And so instead of writing from 1 to infinity here, I'm going to leave this as like a little t, and I'm going to say, well, hey, what is this as t approaches infinity? This is how we get past, we can't treat infinity like a number. We can't actually plug it into our equation, but we can take our limit as t is approaching infinity of 1 over x dx, which we actually know our antiderivative of that is just ln of x. I'm still going to have my limit as t approaches infinity right here. And I'm also evaluating this from x equals 1 to t. So if I plug in t here, and I plug in 1 right here for my bounds, well, ln of 1 is actually just 0, but as t approaches infinity, ln of t is also just going to get bigger and bigger and bigger and bigger. Think about like our graph of ln, it's just going forever in that direction. So this is also going to approach infinity. We call that infinite, or it diverges. This next example is kind of wild because it's very similar to what we were just talking about for Gabriel's horn. So here's our 1 over x. We're just looking at this from 1 all the way out to infinity. And if we rotate that along our x-axis, so we rotate that along our x-axis and try to find this volume. Now, already remember that this, when I'm looking at just the area underneath this curve, that is infinite. But when I look at the volume that is created by this curve right here, that may not be the case. So we're doing our washer method, and this depends on what our x value is. So when I'm doing my bounds from 1, instead of to infinity, I'm just going to put t, and I'm going to say my limit as t approaches infinity right here. Of my equation, that's my radius. 1 over x is my radius, so it's going to be pi and then 1 over x squared, because I'm adding together all of these circles that I have along here. Okay, so I can actually bring my pi out in front of my limit, but I'll just bring it out in front of my integral that I have here. This is x to the negative 2. So if I take my antiderivative of that, I will get x to the negative 1 because I'm adding 1, and then dividing by that new exponent. And I still have my limit as x is approaching infinity right here. This is from x equals 1 to t. So if I plug in those values, I'll actually get this because x to the negative 1 is 1 over that x, and I'm plugging in t and 1. And this actually reduces down to something kind of interesting. So this is as t gets bigger and bigger and bigger, over right here, this 1 over t, I'm actually going to be dividing by a bigger number. So 1 over a million or 1 over a trillion. This is going to be approaching 0. So if I look at my limit as t approaches infinity, I have 1 over a huge, huge, huge number that approaches 0. This is actually just going to approach 1. And I forgot about my little pi that is chilling out in front of all of these things. So that also gets multiplied by pi. This has a volume of pi, but the area underneath this curve is infinite. So crazy. Okay, taking a look at this next example here, we are actually looking at our bounds from negative infinity to 0. So I'm still going to do my little limit trick, where I take my limit as t is approaching, in this case, negative infinity. And that's where my t will go of this whole function that I have here. And I just pulled up our formula sheet because this integral actually looks really, really similar to our tangent inverse function that we have right here. So I just need a 1 plus, and then I can kind of substitute anything in for my x. So I need to force this to kind of be a 1 here. In order to do that without actually changing my equation, whatever I multiply down here, which is going to be 1/4, to really cancel out this 4 right here because I need a 1, I'm also going to do that on my numerator as well, and then that 1/4 can kind of come out in front, but I'll just leave it there for now. And then I have a 1/4 x squared. So a 1/4 x squared is going to be the same thing as x divided by 2 squared. And now that I have it written like this, now I can actually use my tangent inverse as my antiderivative. And I'm going to do a quick u substitution in order to do that. So I'm going to let u actually equal my x divided by 2, and that means my derivative of that is going to be just 1/2 dx. So to solve for that dx, I'm going to multiply both things by 2, and that's actually what I substitute in over here. When I double my 1/4, I will get a 1/2, and that's what I can actually bring out in front of my integral. And then the rest of everything will just be my tangent inverse of u. Okay, so to plug in my x equals d, I actually don't have an x quite here, so I'm going to resubstitute in my my x over 2 for my u. And now I can substitute in 0 and then minus whatever I get when I substitute in t. So for this first chunk, I just have tangent inverse of 0, and if I think about what my angle would be, that my ratio would end up being 0. Tangent is sine over cosine, and so my sine value would have to be 0, and that happens at 0. So this whole thing actually just becomes 0. It's also my unit circle. And I actually want to look at the graph really quick for tangent inverse, or arctan. Okay, so in Desmos, it doesn't really matter whether you use tangent inverse or arctan, they are the same thing, and I'm trying to find my limit as what's inside of this gets bigger and bigger and bigger. The divided by 2 isn't going to really impact it that much. Sorry, I'm actually trying to see it as it's getting smaller and smaller and smaller. It's approaching negative infinity. So as what's inside of here, my x value approaches negative infinity, this is getting closer and closer. If you actually remember some things about just the tangent graph, I think this is getting closer and closer to pi halves. But it would be a negative pi halves since it's going towards negative infinity. So I have a minus negative pi halves, and those two negatives will cancel out. I get my 1/2 multiplies that, and I have pi fourths as what it is converging to. So it converges to actually a number there. Okay, on our next example here, we're actually going to break this up into two different integrals. So my first integral is going to be from what was negative infinity to 0, but my negative infinity I'm going to write as a t and then take my limit as t actually approaches negative infinity of this whole thing. And my other function is going to be from 0 to infinity. Again, instead of infinity, I'm going to have a t, and then I'll take my limit as t is approaching infinity of this whole thing. And now we actually have a function where we can take our antiderivative of it, plug in 0, plug in t, and then discover what our limit is going to be. I think we have to use, well, u substitution will not work, integration by parts. So this one, not too bad to let be our u, because when I look at u prime, it'll just be 1. So derivative of x is just 1. And I'll let this be my v prime. So u prime is just 1. My v prime is e to the x. So my v function, antiderivative of e to the x is just e to the x. And now I can still take this whole thing of my limit as it's approaching negative infinity of, and let's see, it's u times v for integration by parts, so x times e to the x minus my integral of v and then u prime, which is just going to be an e to the x dx. Now that I've actually taken my antiderivative of that, I'm going to go ahead and plug in 0 minus whatever I get when I plug in t. Okay, this is where some funky things kind of happen. So this first term, 0 times e to the 0, cancels out. But I do have a negative e to the 0, which is just a negative 1 right there. And then now, in my next little chunk, this is the part that my limit is really actually talking about. So I'm taking my limit as t is going to be more negative and more negative and more negative. So what I'm going to do here is we actually call this indeterminate form, which is another way of being able to use L'Hopital's. L'Hopital's, if you don't remember, stuff has to be an indeterminate form, which is like 0 over 0, infinity over infinity, and it's plus or minus infinity over plus or minus infinity. So when stuff is in indeterminate form, we can take the derivative of the top and the bottom. So if I think just about this the e to the t right here, so if I'm taking my limit as t gets more and more negative, my e to the t, so I'm just looking at this part right here, is actually going to be approaching 0. So this chunk actually approaches 0. So really what I'm looking at is taking my limit of my t times e to the t, and this is what is indeterminate. I just have to kind of change it a little bit. So how I change it, so like over here to the side, how I'm going to change this is it's already, if t is approaching negative infinity, it would be negative infinity on top over, and then e to the negative t, if I drop that e to the t from my numerator to my denominator, and this is now going to be approaching negative infinity as well. So now I can actually take, L'Hopital's rule says I can take my derivative of the top and the bottom. So derivative of the top is just 1. Derivative of the bottom is a negative e to the negative t because of chain rule. And now I can actually bump this e to the negative t back up to my numerator, and I'll just have a negative e to the t. That is what I can now take my limit as t is approaching infinity of. So negative e to the t, which it's approaching negative infinity. As t approaches negative infinity, that's like on this part of my graph, it is also still approaching 0. So this chunk goes to 0, and I am just left with a negative 1. So this half of my improper integral actually converges. So if this other half of my improper integral also converges, then we can say the whole thing converges. But if this one diverges, it goes to infinity. I add an infinite number of things with something that's finite, the infinite is always going to win. So now we really have to test the second part of our improper integral. So luckily for this one, since we've already done integration by parts, I can actually keep this the same, except now t will just be approaching infinity, and I'm looking at like this chunk down here once I've done integration by parts, and what I'm plugging in is now my lower bound, so x is going to be 0 and x is going to be t. So my part here in orange, when I plug in 0, ends up becoming a -1, and I have a minus right there, so that'll actually end up being a +1. Now if we look at this function right here, that is still going to be something infinite minus something infinite. So I'm going to use L'Hopital's rule, but I have to get it into that indeterminate form where it's either infinity over infinity or 0 over 0. So the first thing that I'm going to do is actually, this is like to the side, I'm trying to force this to be an indeterminate form. I'm going to factor out an e to the t, and when I do that, I'll be left with t minus 1. And now I'm going to put that e to the t to my denominator. So if I'm really looking at this as t is approaching infinity, my top part will be approaching infinity, my bottom part will also be approaching infinity, so I can take my derivative of the top, which is 1, over my derivative of my denominator, which is negative e to the negative t, and I will get a negative e to the t right there. So if we're looking at that as our limit is approaching a positive infinity, we can see that the area that is underneath the curve, even though it's going to be negative, it's still going off towards negative infinity, so we call that divergent. So even though only one of these converges, the fact that this one diverges, so this one goes towards negative infinity, it diverges, both of them are going to. Like the bigger thing overtakes the smaller thing. Our last example is not too bad. I'm going to set it up in that same way where we're taking our limit as t is approaching infinity and then replacing my positive infinity up here with a t. We already know what our antiderivative of that is. It's going to be negative e to the negative x. Don't forget I have my limit of t approaching infinity in here, and then evaluated from -3 to t. Let's plug in t, let's plug in -3, and then we'll look at our limit. Okay, simplifying this down, I get a negative e to the negative t plus an e to the third, and I'm going to look at e to the negative t right here, or negatively see that your y value is approaching 0 because there's an asymptote right there. So I have this chunk approaching 0, and my e to the 3 is just kind of a constant, so my limit doesn't really matter here. It's just going to be approaching e to the third, which means this one converges. Okay, the other way that we can actually use these improper integrals is when we have something like an asymptote at those values. So we can split up our integrals and then we can actually see what is happening as it is approaching either from the right or from the left. And so even though here our integral from 0 to 4, it doesn't have an infinity, you can actually still see that if you set this denominator equal to 0, which we can never ever divide by 0, that x can just not equal 4. And so this bound is where we're having our issue. That means that I can take a look at my limit as it is approaching 4, as my t value is approaching 4, but I need to be approaching 4 from not above it, but from below it, because I'm just looking at my bounds from 0 to 4. So if I'm approaching from what we call the left-hand side, or a left-hand limit, I'm going to have a little negative right there, and that is going to be what replaces my t on this side. Everything else kind of stays the same. I think it's possible to use some u substitution here. If I let this bottom part, my 4 minus x, if I let that be my u, that means du is just equal to -1 dx. And I can divide that over to just have a negative du. So my dx right here is going to become a negative du. I put my negative out in front of that integral. I'm going to bump my square root of u up to my numerator and change it to be a u to the -1/2. Then I can take my integral. So integral of u to the -1/2 is going to be u to the 1/2. I'm dividing by 1/2 or multiplying by 2. And now I just need to resubstitute what I had in for u over here. So I'm going to replug in 4 minus x for my u. And even though I'm approaching this from my left-hand side approaching 4, I can actually just still plug in my t and my 0 here for my x, and then let's take a look at the limit. Okay, so over here I can actually solve this out. I have 2 negatives, so that's going to become a positive. 4 to the 1/2 is the same thing as square root of 4, so this whole chunk will just become 2. And then that didn't depend on my limit, but this part does depend on my limit, and if I plug in 4, so just direct substitution, if I plug in 4 for my t, I'll end up getting 0, well, the square root of 0 is just going to be 0. Once I multiply that 2 by my constant 2 that was out in front of here, my final answer will just end up being 4 because that part was 0. We're actually not going to work out this entire next problem, but I wanted to talk about how to kind of set it up. So this next problem does diverge, and we are going to set it up into 2 values because this has an asymptote right there at 0. We're going to set it up into 2 values, 2 integrals. This one will be approaching from the left, and this one will be approaching from the right, and both of those end up diverging when we follow that through. Sorry y'all, I am fading fast, and I'm even drinking a cup of coffee, aka tears of my students. The last 2 examples that I wanted to talk about were done with what we call the comparison test. So our comparison test is saying that if we can compare this integral to something that we know converges, or we can say that it's less than something that converges, then it does converge. And if we could say something is more than a function that does diverge, then we can say that the original function diverges. So this right here, really the ones that we could compare it to are 1 over x and 1 over e to the x. So if I kind of like break those up, and I just want to like think about each of these. So we're trying to show that this converges, so we need to show that it is less than one of these. Our 1 over x isn't really going to help us because we know that that one actually diverges. So, but we do know that this 1 over e to the x does converge, and so I just need to show that this function is less than 1 over e to the x for every value of x. So I want to start out with an x value of 1, and then we'll also do an x value of 2. We're just trying to like see if this is true. So for an x value of 1, I have 1 over 1 and then e to the 1, and that is my function right here. I want to compare it to my 1 over e to the x. Okay, so right now those things are for sure equal. Now I want to try that when x is equal to 2. So over here I'm going to have 1 over e squared, and I'm comparing that to this function right here, and so I have 1/2 of what's in my purple. That is going to be strictly smaller than, but we could say less than or equal to. And that's just going to keep on happening. I'm going to have 1/3 of that function. I'm going to have 1/4 of that function. So this function right here, my 1 over x e to the x, is always going to be smaller than my 1 over e to the x, which I know that this actually converges. This is the idea of we're comparing functions. So just to make sure, I'm actually going to take this 1 over e to the x and make sure that this truly does converge. So I just wrote this as an improper integral with my limit as t is approaching infinity and replace my infinity as a bound with t. Now I'm going to take my integral of e to the negative t. Looks like all I need to do now is plug in t minus whatever I get when I plug in 1. So my first part is negative 1 over e to the t, and if I look at my t approaching infinity, it's the same thing that happens in this graph right here. As it's approaching infinity, this is actually approaching 0. So this chunk is actually going to be approaching 0, and then I'll have a plus, because I have 2 negatives, 1 over e. That is what this is going to be approaching, so it does converge, which means that anything less than it, this function right here, also converges. Last example, if we have a function right here that is always larger than a function that we know diverges, then that forces this function to also diverge. So really the functions that I could compare it to are 1 over x or ln of x, and I want to make sure that this function right here is always going to be bigger than or equal to one of these. So if I choose ln of x, the second I start dividing by x, that's actually going to get smaller. Ooh, but if I choose 1 over x, so I'm really comparing it to this function, e to the positive infinity, 1 right here is always going to be smaller than ln of x as long as x is bigger than e, which that's what we're doing. We're looking from e, and then as e gets bigger. So all I need to show is that this function diverges, and then I'll know that the function I'm actually trying to find diverges really does. So I'm going to take e to the infinity. I'll write it as a t instead. So as t approaches infinity of 1 over x dx, and that is going to be ln of, and I'm just going to straight up plug in my t and plug in my e, and I am taking my limit as t approaches infinity of these things. Well, ln of e is still just 0. And then ln of t, as t gets bigger and bigger, this is also going to diverge. So that means my original function diverges because it is always bigger than the function that I showed diverges. Okay, y'all, hope you have a great day. Bye.